In this video of Unit 15, we focus on the magnetic field generated by currents. In the first part, we will explain what is this magnetic field provided by an element of current, which is called the Biot-Savart law. And then we will show several applications to highly symmetric currents, which are the loop, solenoid, or a straight wire carrying current. So before beginning, I want you to remember in Unit 14 that when we were looking at what was the force exerted on a charge that was moving inside a magnetic field, and this force was given by the magnitude of the charge times the cross product between the velocity of the charge and the magnetic field. And if you remember, from there we derive an expression to see what the amount of force was exerted on an element of current. And from this expression of a point charge, we got to the expression for an element of current. And this was the expression. So in this change, from the force provided on a charge to the force provided on an element of current, we modified and going from Q times V to the electric current times the element of that was giving you the direction of this current, what we call the current element. So here we're going to do the same thing, but quicker. We're not going to deduce it as slowly as we did in Unit 14. So we're going to go from what is the magnetic field generated by a point charge with a charge Q that is moving at a velocity V at a point that has a distance R to this point charge, and we're going to provide what is the differential magnetic field provided at a point P, okay, at this point P, by this current element. So we're going to change from QV to the current element. So this is going to be mu sub 0 divided by 4 pi times the current, the electric current, times the differential of path, and this differential of path that has the direction of the current, really, because it's the vector that has this, times the cross product of this direction with the unit vector that gives you the distance to the point. Okay, so if you see, we've only changed this part here, and this is what is known as Biot-Savart law. So you have it in the slide here. You have it a bit more, a bit cleaner. Okay, so that is the amount of magnetic field provided by this little current element. If we want to know the total magnetic field provided by the whole current, what we have to do is to integrate. Okay, integrate the magnetic fields provided by each little segment of the current. Okay, so once we've seen the Biot-Savart law, we're going to apply it in several cases. So one of the most simple is the current loop. So here we have a loop. Okay, this is just a circular wire, if you want, that has current going through it. Okay, so we want to know what the magnetic field is generated in its center. So point P is here in its center. Okay, so we begin by Biot-Savart law, and we calculate how much magnetic field there is in this point here. So we have to begin by discussing we're going to begin discussing just a small element, and once we have that, we're going to integrate across all of the loop. Okay, so we're thinking, first of all, we will do this, but first of all we're going to focus on the differential of magnetic field. So we focus on this small element, and we see that this vector, this differential vector that's giving you the direction, is perpendicular to the unit vector in the direction of the distance to the point where we are suffering this magnetic field. Okay, so we can just say that the amount of magnetic field provided there is going to be mu sub 0 divided by 4 pi I dl square r, because you know that this is equal to 1, okay, because it's a unity vector. And then to discuss the direction, you need to see what is the plane where both this vector here, the differential vector with the direction of the current, and the unity vector are contained. And if you see, this is the vector, in this case is the plane yz. Okay, so the cross product between these two vectors has to be in the x direction. Okay, so and then to know if it's in the positive x direction or in the negative one, you can use your right hand. And for it, you would have to put in your index the differential of current that is going towards the positive side of the z direction, and then in your middle finger the vector r, this vector here, and this makes your thumb point towards the positive direction of the x-axis. So that is why this is here with a positive direction. So once we have this, we just have to integrate. And in this case, this small r that I was putting here is really big R, which is just the radius of the radius of the loop. Okay, so here it's a very easy example, because whenever we integrate, R is not going to change, and all the vectors have the same direction. So this simplifies to just doing this very easy calculation, which is just knowing what is the complete perimeter of the loop, which is just 2 pi multiplied by r. So if you put everything together, this is for the entire magnetic field. Okay, so this is the integral, and then you can see that this is going to give you mu sub 0 divided by 2, because the 2 pi divided by the 4 pi leaves you a 2 here. This is I, and this is just an r. Okay, and this is the positive direction of the x-axis. Okay, so here you have it also in this slide. Okay, and then we can discuss what it is in its axis. Okay, so now we're not in this point here, but we are in any point in the axis, for instance in this point here. So we would have to discuss again. And if you see, in this case again, the element of current and the unity vector in the direction of r are both perpendicular. Okay, so that makes very easy the calculation of the cross product, of the modulus of the cross product. The only thing is that now the vector, this differential of magnetic field, has to be perpendicular to both, and as it's perpendicular to r, it has this direction here, so it belongs to the xy plane, but it's perpendicular to this vector here. Okay, so so it has this direction. Okay, we could integrate both components, the x and the y component, but we can also derive that if we do the same calculation for a point here, this would be the dl, and this is the element of current. It would provide us with the same magnitude of magnetic field, with the same components x and y, except that the y component would be towards the negative side of the y component of the y-axis. So at the end, we can say that the total magnetic field in its axis is going to be just the the component on the x-axis because of symmetry. Okay, so then we can just derive. We will just need to know what is this component, and this component is going to be the modulus times the sin of this angle here. Okay, which is the not this angle here, the angle between so this is cosine of this angle, which is equal to the sin of this angle here. Yeah, this one. Okay, so it will be the cosine of this angle, and this angle is the cosine of this angle is like the sin of this angle here. Okay, so we would just have to integrate this. Well, first derive this expression, and as I was saying, this is if we do this, then this small component, this differential magnetic field in the x component is going to be equal to mu sub 0 the current divided by 4 pi, and then this has to be the element of current, okay, the L divided by the square, here we go, the square, this distance here, times the sin of theta. Okay, so this r is equal to square big R plus square x, the square root of this, because this distance is r, this distance we're going to call it x, so this is this here. So if we put everything together, we can see that this component here is equal to mu sub 0 divided by 4 pi I. This is the sin of theta is equal to r divided by square r plus square x 1/2. So this I put here, this r, and this is square r plus square x 3/2. Okay, and then this is the L. Okay, and then we just have to integrate this to get the whole magnetic field. Okay, we just have to integrate this component, and this integral is very simple because it is not going to depend. R and x are not going to change. So when you do this integral, if you do this integral and you get this is going to be 2 pi times r. So this gets very simple, and at the end you end up with this expression for the magnetic field provided by a loop on its axis. Okay, for the directions, there is a rule where you can easily remember what the direction is going to be. So to use this rule, you have to get your right hand and you have to manage to go along the loop with your 4 fingers in the same direction as the current. So you have to get the loop pointing the current, your index, middle, and the other 4 fingers, the whole 4 fingers in your hand have to go making a loop in the same direction as the current, and then your thumb is left pointing towards the magnetic field. So if these are your fingers, this is the small one, okay, they both all of them have to be pointing like this, so your thumb is going to be left here. So it's signaling that the magnetic field is going to have this direction inside the loop, okay, and all across the axis, okay, it's going to have this direction. Out of the loop, the magnetic field looks like this. Remember that the magnetic field, the field lines they don't have a beginning or an end, so they're just going round and round, okay? So from this loop, we go to a different device, which is a solenoid. So a solenoid is just a very long wire that is going round and round many times. So this is how it looks. So we're going to call here L to the length of the solenoid, and we're going to say that it's gone round and round this length n times. Okay, so that's like having big N loops. Okay, that we have many loops. So the amount of loops per meter, this is going to be given by this small n. So small n is big N divided by n. This is the let's say the linear density of loops. Okay, so we can see the solenoid as constituted by many loops. Okay, so we can bring what we just learned from a loop and think that instead of having a loop, we have many loops, and we're going to integrate the magnetic field provided by many loops. Okay, so imagine that you want to know the magnetic field at point P here. Okay, so X is going to be the position of this point P, and then A is the beginning of the solenoid. B is the end of the solenoid. And we're always going to think that the solenoid is very long. This length here is much bigger than this length here, okay? Because this is going to let us do some approximations. So we bring back what we already knew. If we only had a small solenoid provided with this given by this small thing that I'm plotting here, which has a length differential of x, then the magnetic field provided by this by this loop would be mu sub 0 divided by 2 times square r divided by square r plus square x 3/2 times differential of E, okay, this is just the amount of charge, of current that is going around here, okay, and this differential of E is really equal to the amount of current that is going through just one loop times all the loops that are provided in this little segment, which is going to be the length of that segment times the amount of loops per meter. Okay, so this is going there. Okay, this integral is a bit more tricky than the other one. So you can derive the integral and make it, and you can follow the books easily to derive the integral. And the idea is that that if the current is going in this direction, then applying your right hand, the magnetic field is going to go in this direction, okay? Because it's just a matter of adding a lot of loops, and they're all contributing in the same direction. So I'm going to just jump all the demonstrations and tell you that this is the final expression you get, okay? So where x is providing the point where you are suffering where you're calculating the magnetic field, okay? So this is x, this direction here, this length here, and A is the beginning and B is the end of the solenoid, okay? So this is the result of the integral, but we want to know it at a certain place. Okay, so we want to know for points that are well inside the solenoid and away from the ends. Okay, so we're going to simplify this, saying, okay, away from the ends, I'm going to say that I'm going to place my axis in a way that the left limit, which I call A, is equal to minus L/2, and my right limit is going to be equal to L over 2 because the total length is L, okay? And I'm going to say that away from the ends is approximately in the middle of the solenoid, okay? So if you place these three things, you end up showing that the total magnetic field at that point x equals 0 is going to be mu sub 0 times n times the current divided by 2 times, and here what we have is 0 minus minus, so this is L over 2 divided by L over 2 square plus R square. This is the square root of that, minus, and this is minus L over 2, so that's a plus, and here you have L over 2 square plus R over 2, and this is 1 over 2. Sorry for the ending there. So here the idea is that L is going to be much bigger than R. So I'm going to divide, at first you see that these two expressions are the same, this and this, so we just can say that this is going to be equal to mu sub 0 n y divided by 2 times twice this expression here, one of these expressions here, and here I'm going to divide both by L over 2, so this is equal to 1 over 1 plus square R divided by square L and times 4. So this is, in this approximation of L much bigger than R, this is approximately 0, okay? So this is approximately 1, so you end up showing that this is the magnetic field away from the ends, is in the middle is going to be mu sub 0 times n times the current, okay, in the direction, in the x direction. And this is what you have in this part in the slide. So away from the ends, so this is like this. If you one of the ends you can derive on your own, just saying that A is minus L over 2, B is equal to L over 2, and that X is equal to L over 2. And then you will come up with this expression here. So it's quite interesting because if you show the whole magnetic field as a function of the distance between both ends, you end up with one of these graphs. So this is the magnetic field, okay, and this is the distance. This is x for our case, okay, and this is 0. This is the center of the solenoid where you have this amount of magnetic field, and then when you go away from the center, this value does not decrease much. It only decreases when you are very close to the end, okay, and when you're very close to the end, in this point here, okay, this is just half of what you had before, okay, this is half. This is just half the value. So so whenever you are in a solenoid, in a long solenoid in which the radius is smaller than the length, and you are in the interior away from the ends, it doesn't matter if you're exactly in the center. It doesn't need to be exactly in the center. It can be away from the ends. The magnitude of your magnetic field is going to be quite constant and equal to this quantity here. So and out of the solenoid, the magnetic field is much weaker. You can see it here. Approximately the magnetic field lines of a solenoid. So in our case, we can use the same, to know the direction, we use the same rule of the right hand. We go through the solenoid with our 4 fingers in the same direction of the current, and then our thumb is left pointing towards the magnetic field inside the axis, okay? So in this case, you can see that our fingers would be like this, okay? This is the rest of our hand on the other side, and then our thumb is left going like this because we're thinking that the current is going like this in the wire. So it's going up on this and the side we don't see, and going down in the side we see. So this means that the magnetic field in the interior of the solenoid has the direction. So from here, I want you to remember. Well, sorry. Before summarizing, I want to tell you that the solenoid for magnetism is like the capacitor for the electric field. So if you remember, when we had a parallel plane capacitor, the electric field between the plates was constant, and outside the plates was zero. Well, with the solenoid, it's a similar example, but for the magnetic field. So the magnetic field inside the solenoid is away from the ends, has this expression, and out of the solenoid is very weak. Okay, so you can see here that the magnetic field lines are quite separated with respect to how pressed they are inside. So from this part, I want you, and I don't need you to try to remember how to derive the expression, but I want you to remember this expression here. Okay, the magnitude of the magnetic field provided by a solenoid on its interior away from the ends is going to be mu sub 0 times small n, which is the number of loops per meter that we have, times the electric current. And I want you also to know the direction. So for that, you need to use your right hand and go along the solenoid with your 4 fingers. So the thumb, the 5th finger, is going to point towards the direction of the magnetic field. Okay, so this is what I want you to remember from this. There is another example also relevant for the applications we're going to see, for instance, in the problems, which is the straight wire. So for the straight wire, we just show here a length of straight wire that goes from x1 to x2. So it goes from here to here. It's this yellow line here, and the direction of the current is given by this direction here. Okay, so we want to know what the magnetic field is provided in a point P that has a distance that is at a distance big R from the axis of the straight wire. Okay, so to do this, we will have to apply again our knowledge of the Biot-Savart law, and then we would have to begin by trying to know what the direction of the magnetic field is. So in this case, we take a piece of the wire. This is going to be the element of wire, the element of current. Sorry, this is I DL. Okay, DL is the differential length of wire that which I'm using to calculate the differential magnetic field at this point P. So this, and then R is this vector here. Okay, so we know from the Biot-Savart law that the amount of magnetic field provided by this element of current at point P is going to be mu sub 0 divided by 4 pi times the element of current cross product with the unity vector of R, and divided by the square of the distance. Okay, so here we can see that that both the current element and the unity vector, or the R, both belong to the plane of the screen. So we can derive directly the direction of this differential of magnetic field. So the direction of this magnetic field has to be perpendicular to the plane provided by the vectors for which you are calculating the cross product. So it has to be a vector that is perpendicular to the to the screen. Okay, to know the direction, you would just have to use your right hand side, put the index on the direction of the element of current, your middle finger in the direction of the distance, and then you're left with your thumb pointing away from the screen. So that provides a magnetic field that is perpendicular to the screen and going out of the screen. So we can represent it by a point. Okay, so we already know the direction. And the other thing we would want to know is the magnitude. Okay, here realize that all of the elements of current all of the different elements of current are going to provide the same direction and for the differential magnetic field. So in this case, we're going to be able to say that the total magnetic field is going to be equal to the modulus, and this is the direction, and that the total magnetic field is going to be really the integral of this in this direction. Okay, this is a simple case. So we can just focus on the modulus of this differential magnetic field. So let's focus on this module. So this is going to be 4 pi divided by, mu sub 0 divided by 4 pi. This is going to be I, and in this case, as the element of current is in the x direction, we can just provide this as differential of x. And then we have to divide by the square of the distance that we're calling r. And then there is a difference here that from the previous example, and it is that the differential of x, the element of current, is not completely perpendicular to the distance. So we have to take into account the sin, okay, of the angle they form. This is the angle they form, okay? So this integral is going to be more simple if you use the following. If we, instead of trying to integrate in x, we integrate in using this angle theta. Okay, we're going to use theta, and we're going to try to integrate from theta 1, that is consistent with x1, to theta 2, which is consistent with x2. Okay, so first of all, the relation between this angle here and theta is just that the sin of this angle is equal to the cosine of theta. Okay, then we also want to put r as a function of theta, and also differential of x as a function of theta. So to put r as a function of theta, we can say that r is equal. It's going to be easier to explain. We can say that cosine of theta is equal to the cosine of theta is going to be equal to r divided by small r. Big R is this distance, okay, is this here, and small r is this. So the cosine of theta is equal to this. So we can say that small r is big R times So small r is equal to big R divided by the cosine of theta, okay? And the other element we have to put in as a function of theta is differential of x. To do this, we can say that the tangent of theta is equal to x divided by r. So x is equal to r tangent of theta. So from here we do the derivative, and we say that the derivative of x is equal to r. The derivative of the tangent is 1 over the square of the cosine times the derivative of theta. So with all these elements, remember we have to put them together in this expression. So we have to, instead of using sin of this angle, we're going to use the cosine of theta, because we have this. Instead of using differential of x, we're going to use this expression here. And instead of using square r, we're going to use this expression square r. So if we do all this, if we do all these things here, we end up with the following expression. So we would say that differential of the magnetic field is going to be equal to mu sub 0 divided by 4 pi times I, and then here instead of 1 over square r, we would put the square cosine divided by square r big R, okay, because I'm using this here. Then instead of differential of x, we would put the differential of theta divided by the square of the cosine, because instead of using this, I'm using this. And instead of the sin of this angle, I'm going to put the cosine of theta. So this leaves you with differential of b being equal to mu sub 0 and the current for pi, and here we just have to have 1 over square r, big R, times cosine of theta, differential of theta. And this is what we have to integrate between theta 1 and theta 2. So this integral is sorry, this is not from theta 1. This is the whole integral over the magnetic field. This is from theta 1 to theta 2. And this, if you do this integral, well, you just find that this is the sin, okay? The most interesting case for us is going to be when this straight wire is infinite. As you know, anything is not, there's nothing really infinite in our lives, but a length of wire can become infinite if we get very close to it. So if I'm at this point, this wire here plotted here is not infinite at all. But if I'm very, very close to it, this dimension becomes much bigger than this dimension here. So this becomes like an infinite wire, okay? So whenever we say infinite, it's just that we are much closer to the wire than the total length of the wire. So for an infinite length of wire, this theta 2 tends to go to pi over 2 and theta 1 goes to minus pi over 2, okay? So this goes to 1 and this goes to minus 1. So you end up having, for an infinite wire, you end up having this expression, twice this expression. So this is what I plot here. This is the magnetic field for an infinitely long wire, okay? And here to remember, so from all of this, I want you to remember this expression here. It's going to be important for us, okay? So try to remember or have it, write it somewhere, okay? And what's going to be also interesting for us is to try to remember the direction. So you could go and derive the direction as we did before with your right hand, or you can use a mnemotechnic technique, which is taking the wire, going to the wire, handing the wire with your thumb pointing towards the positive, towards the current. So that is why the thumb is pointing upwards, because the current was going upwards. So then our fingers are going to give you the direction of the magnetic field at the different points. So at this point, the magnetic field is going to have this direction because your fingers would be like showing this direction. At this point, the magnetic field is going to have this direction. At this point, it's going to have this direction. Okay, so if you go from above, and this is the wire seen from above, and the current is going out of the screen, then the magnetic field at this point, at all points that have the same distance, big R, is going to be the same in magnitude and in direction. If you put your hand in a way that your thumb is going out of the screen, then your fingers will be holding this wire, giving you this direction. So this is the direction of the magnetic field provided by a current that is going out of the screen, okay? And the magnitude is given by this expression. So this is what I want you to remember. Okay, and there's just one last thing I wanted to talk about, and it's the force between currents. Okay, so here we've seen in this unit 15 that a current or an infinitely long wire, or even if it's not infinite, it will provide you, it will generate a magnetic field around it. Okay, but in unit 14 we saw that a current inside a region where there was a magnetic force, a magnetic field, it suffered forces. So there was a magnetic force exerted on a wire that was inside a region where there was a magnetic field. So this is what we have if we have two currents. So imagine these two currents. This is the first one. This is the second one. So to the first one, I'm going to call I1, that is the magnitude of the current of the first wire, and I2 is the magnitude of the current of the second wire. And they're both at a distance r, okay? They're both parallel, but at a distance r. So from what we've just seen, we know that this this current is going to generate a magnetic field all around the region. And in particular, in this point here, it's going to create a magnetic field provided by this expression. So it's going to be mu 0 divided by 4 pi, 2 times the magnitude of the current that is creating the magnetic field at this point here, okay, divided by r, which is the distance between both wires. So to know the direction, you have to apply, as I told you, your right hand and go take the wire and put your thumb towards the upper part of the screen. So that leaves you with a magnetic field that is really going into the screen in this point, which is this is what we are trying to represent here. Okay, so now that we have a magnetic field that is going that is having this direction, it's entering the screen at each point here. We know that here there is another current. We know from Unit 14 that there is a force, a magnetic force exerted on wire 2 because there is a current in wire 1. And this magnetic force is the force exerted by the first wire, by the first current on the second current, is equal to the intensity of the second current, the element of current of the second current, the cross product with the magnetic field created by the first current, okay, which is here, and which the direction we know is like this. So if you solve for the directions, you know that your element of current is going to go towards the upper part. You know that you should place your index finger in that direction. Then you should place your middle finger going into the screen, and this leaves your thumb, your right hand thumb, pointing towards the left. So this means that if you have two currents that are parallel and they have the same direction of the currents, there's going to be a force exerted by the first one on the second one that is going to try to push the second one towards the first one. I'm not going to do it in this video, but you can redo all this same calculation, thinking that the second one is the one provided a magnetic field and the first one is suffering, and then you will end up not showing that then over the first one there is a force towards the right. So when both currents have the same direction, the forces are attractive, and you can also deduce that if they have different direction, the forces are going to be repulsive, okay? And that is for directions, but we can also work a bit more the magnitudes. So we know that these two are perpendicular, and we've also discussed the direction, so we can say just that the amount of force on the element of current in the first one is going to be the current of the second one. The force provided by the first one on the second one is going to be equal to the current of the second one, this element, times the magnitude of the first one, which it's provided here. So this is 4 pi, mu 0 divided by 4 pi times twice the current of the first one divided by r, which is the distance between both. Okay, so of course, if the currents are infinite, because this was for an infinite wire, finally the forces are infinite because this would be infinite. So we cannot just calculate the total force of the wire, but we can calculate the amount of force per length. We can calculate the amount of force per length. So this is the amount of force exerted by the first wire on the second per length of the second one, and this is going to be mu 0 divided by 2 pi times the current of the first, current of the second, divided by the distance between both. Okay, so this, you have it a bit more clean here, and you can either remember it or try to deduce it from this one that I would like you to remember, and from this that we also learned in Unit 12. And just to remind you that if they have the same direction, the forces are attractive, and if they have opposite directions, the forces are repulsive. And also wanted to tell you that This is used to define the unit of current, which is the ampere.